BigSmall, efficient multitask learning for disparate spatial and temporal physiological measurements. Video presentation. This work is conducted by researchers at the University of Washington and the Massachusetts Institute of Technology. Human visual perception occurs at varying scales. Attending to coarse spatial information enables fast estimates, while attending to fine spatial features enables slower refinement. These scales of perception have historically inspired the design of computer vision architectures which mix these spatial-temporal scales. Similarly, physiological changes are also exhibited at varying scales on the body and with modality-specific properties. In this project, we focus on the human pulse, respiration, and facial action, which is the analysis of muscle activations on the face, which correspond to a number of downstream emotion tasks. Here we can see that these signals have very disparate spatial and temporal scales. The human pulse is fast, highly periodic, and requires gross spatial features to be sensed. It can be sensed from the entire body. Facial action, on the other hand, is slow, sporadic, and requires highly detailed spatial scale. It can only be sensed from very specific points on the face. Respiration falls between these two modalities, being moderately fast, somewhat periodic, and requiring moderately detailed spatial features for sensing. It can be sensed from specific areas on the body, specifically the head, chest, and abdomen. Though these cardiopulmonary and facial action signals seem to have differing spatial temporal representations, there are similarities. These signals are all controlled, in part, by the autonomic nervous system, and these signals can all be measured through examination of the human face. Thus, although the low-level feature representations differ, it may be possible to concurrently learn these signals from a single input modality, such as face video. This begs the question, can we learn these signals in a unified representation, and can we make this architecture efficient? Efficiency is critical for applications such as telemedicine, where on-device models enable privacy. To this end, we present BigSmall, a model that leverages spatial and temporal scales, in addition to wrapping temporal shift modules, to efficiently multitask spatially and temporally disparate tasks from video. The network is comprised of a big branch that models low-frequency, high-fidelity spatial features, given high-resolution raw frames, and a small branch that models high-frequency temporal dynamics, given low-resolution difference frames. To improve computation efficiency, BigSmall temporally downsamples inputs to the big branch as low-frequency spatial features change slowly. As compute of the network is driven by convolutions on large big branch inputs, this temporal downsampling results in a significant computational efficiency benefit. Specifically, if the big branch receives 1 frame for every n frames received by the small branch, the computation of the model is reduced by a factor of approximately n. Note that temporal downsampling of the big spatial branch increases load on the small temporal branch to assist in interpolating discarded big branch input features. For this reason, BigSmall introduces wrapping temporal shift modules, or WTSMs, to augment temporal dynamics learned by the small branch without incurring additional computational overhead. WTSMs allow for robust temporal modeling even when training requires a low consecutive frame count or latency constraints are high. In these scenarios, for example, AU model training, WTSMs outperform traditional TSMs by preventing zeroed features traditionally caused by shifting. Here we see a comparison of WTSMs against traditional bidirectional TSMs. We can see whereas traditional bidirectional TSMs shift out features and zero pad the resulting embedding, WTSMs take features that are shifted out and pad areas with zero padding with these features. On the right, we can see an example of WTSMs outperforming TSMs in a PPG model when we have a low number of consecutive frames. WTSMs in this scenario help bring a substantially more robust temporal embedding. We evaluate BigSmall on the spatially and temporally disparate physiological sensing tasks of remote photoplethysmography, respiration, and facial action unit classification. Here we can see an example of BigSmall, which concurrently learns PPG, respiration, and facial action from face video. The predictions from the models are plotted against the sensor ground truths for PPG and respiration and the manual annotation ground truths for action units. Here we see another example. We conduct an ablation study of BigSmall and find that the use of big branch temporal downsampling drastically reduces compute. In our evaluation, where we use a consecutive number of frames equal to n equals 3, compute is reduced by approximately 66%. Our evaluation also finds that the use of WTSMs enable a much more robust temporal representation. Furthermore, these results validate the utility of WTSMs over traditional TSMs and illustrates how WTSM augmented temporals interpolate spatial task features. Additionally, we compare BigSmall against a number of task-optimized models. We validate that BigSmall is able to concurrently multitask PPG, respiration, and facial action with comparable performance to the state-of-the-art task-optimized methods. Furthermore, we investigate the use of task-optimized models integrated into the BigSmall framework. We introduce BigSmall++, which utilizes the JAANet AU network as the big branch backbone. And we find that BigSmall++ achieves accuracy on par with these state-of-the-art AU models while only using approximately 1/3 the compute of JAANet. Additionally, we evaluate the ability of BigSmall to generalize to new data from public datasets and find that BigSmall performs comparatively to these state-of-the-art methods. Here we visualize a number of results previously shown in the tables. As mentioned, BigSmall significantly improves upon the compute of running multiple task-optimized models while still performing comparatively to state-of-the-art baseline methods for each task. Here we have the heart task, the respiration task, and the task of facial action. To conclude, we present BigSmall, an efficient architecture to multitask PPG, respiration, and facial action from face video. We leverage mixed temporal scales and WTSMs to improve compute and augment temporal dynamics. Our evaluation finds that BigSmall is able to concurrently learn these disparate signals with performance comparable to state-of-the-art task-optimized methods. Thank you for listening. If you're looking for additional results and discussion, these can be found in our paper and supplemental materials. Please forward us your questions. Please visit our GitHub for code and our project website, also linked through the QR code, for additional information. BigSmall, efficient multitask learning for disparate spatial and temporal physiological measurements.